Benjamin here. It's almost time to say goodbye to 2025. And if you've been following the Nature podcast for a while, you'll know that around about this time, we like to take a look back at some of the stories we've covered on the show over the past 12 months. In this edition of the podcast, members of the team will each be picking out something they made in 2025 and telling us why it stood out to them. Kicking things off this time round is Nick Petrichow and his choice.
So I was looking back this year on the stories that I've covered for Nature, and I decided to go with one all about potatoes. And it's because they've got some really fascinating genetics and history that we delve into this podcast, and a lot of things that I didn't know before reporting on this, such as, there's not a lot of diversity in potatoes. A lot of potatoes are quite similar in terms of their genetics, despite them looking quite different when they're on our plates. And also, I have slipped in a few references to something or another throughout, so enjoy them when you come across them.
From the 16th of April, here's Nick's highlight from 2025.
First up on the show, researchers have been creating a collected group of genomes known as a pangenome to understand the genetic diversity of the humble potato. This effort could help in the breeding of new potato varieties, such as those adapted to disease or climate change. Now, potatoes are incredibly flexible. You can boil them, you can mash them, and you can even feed over 1 billion people with them. But if you want to make a new variety of them, that isn't so easy.
So compared to other cultivars, potato is particularly difficult because of the tetraploid nature.
This is Sergio Tuso, a geneticist who's very familiar with the difficulties potatoes and the breeding of their different varieties or cultivars pose. You see, the potato is tetraploid, meaning that instead of having 2 sets of chromosomes, like you and I do, potatoes have 4.
So this makes it particularly difficult when it's related to breeding programs, right? So you want to introduce new traits or characteristics, then it's very difficult to put it in the 4 copies of the genome. So that means that the breeding programs in potato has not been very effective, and we have mostly been using the same varieties in the last, let's say, 200 years.
When you cross 2 different parent varieties of potatoes together, it's hard to control which genes you're going to get in the offspring, making it difficult to know what traits you might end up with. And that matters because if it's hard to breed new types, it could make it difficult to adapt potatoes to new challenges, like new diseases or climate change. And that is important because
I guess the first thing is that it's tasty, right? I think everyone likes potato. But probably also very important that it's the food for 1 billion people in the world. So it's one of the most important crops.
So to help this tasty and important crop become easier to breed, Sergio and a team of researchers are writing in Nature this week about a pangenome of different European potato varieties. Essentially a combination of multiple genome sequences that allows researchers to get a sense of where they're similar and where they're different.
And from this, we can sort of predict what is the diversity that we find in most of the cultivars that we consume today.
As it turned out, potato varieties are very genetically similar. So the team were able to capture an estimated 85% of the genetic diversity that exists in these European potatoes by looking at just 10 genomes. Those genomes came from old potato varieties that are essentially the parents of many present-day potatoes. That's in part because of the potato's particular history. Because while they appear on plates the world over now, for thousands of years previously, potatoes were only grown in the Americas before being brought to Europe by the Spanish in the 16th century. This handful of varieties were bred and bred and bred to create many of the huge variety of tasty tubers enjoyed around the world today. And this gave the team an advantage when it comes to capturing most of their genetic diversity.
There's something like 1,700 different varieties of potato grown in Europe today, and that's too many to assemble.
This is Craig Dent, another member of the potato pangenome team. To overcome this, they went back to some of those original varieties brought over to Europe.
We thought if we looked further back in time, we might be able to find the different sets of DNA that have then spread out amongst this population, but get them where they're a bit more concentrated up near the top of the family tree.
And whilst that may sound straightforward, it was quite a challenge, as that complicated genetic tetraploid nature has not only thwarted breeders, it's made things hard for geneticists too. Here's Sergio.
You can picture assembling a genome as a puzzle, right? So you have many different pieces and then you put them together. But in this case, instead of having one, you will have 4 layers of the puzzle in which the figure of the puzzle is quite similar between them. And it's very easy to mix between them.
The complexity of having to solve 4 very similar looking jigsaw puzzles has meant that it's only been in the last few years that a potato genome has been assembled at all. In this instance, the team needed to combine the genomes of multiple varieties in order to make a pangenome. But with improvements in DNA sequencing and some clever techniques, the team managed it. And so, what does the potato pangenome tell us?
The first thing that we found is that when you look at the sequences of DNA, they're actually super, super different, right? So you have extremely high diversity at the sequence level, but actually this diversity is contrasted by the number of unique sequences, which is very, very low.
Now, that may sound a bit counterintuitive, but basically it means that there are very few unique bits of DNA between the different varieties. However, when they are unique, they are very different from one another. Sergio thinks that this indicates that potato varieties lost a lot of their uniqueness when they were grown in the Americas, possibly from the indigenous peoples in the Americas breeding them for desirable traits, or it could just be a quirk of how this species intermixes. Previously, it was thought that because only a handful of potato varieties were brought to Europe, this acted as a genetic bottleneck, removing uniqueness and making subsequent varieties more similar. And whilst the team do see signs of this as well in their research, it looks like potato varieties lost a lot of genetic diversity before the trip to Europe, although more work will have to be done to understand the history of the potato fully. This lack of uniqueness between potato genomes could mean it's even harder to breed new ones with desirable traits, as there's not many new genes that could be introduced, at least through conventional crossing of cultivated types. But because potato varieties are so similar, the team hopes their pangenome can speed up the sequencing of varieties not included in their work, something they tried out with a very popular potato.
And the cultivar that we took for that is this cultivar rice at Burbank that's used by McDonald's for their French fries. You might be familiar. And so we took that cultivar and just using some relatively cheap sequencing, tried to reconstruct its genome, and we found we could put together a large part of it.
Assembling genomes of potatoes very quickly and cheaply is still a way off, but that's the direction the team are moving in. Once that is possible, it could also be possible to identify specific traits that you'd want to breed or even genetically engineer into new or existing varieties. This could be key to making sure we have potatoes resistant to new diseases and the future warmer world they'll find themselves in. One outstanding question is the genetic diversity of potatoes that the team didn't capture. They estimate they got around 85% of the genetic diversity of European potatoes, meaning there's about 15% this work doesn't cover. This may include a lot of DNA that's been brought into modern potatoes in the last 50 years or so. During that time, people went back to the wild potatoes in the Americas to try and find useful traits like disease resistance and bred them into potatoes we eat today. The team are looking to fill that gap, and it's unclear what might be found in those remaining potato genetics. Craig, for one, is excited to find out, and about a whole new world of potato genetics in the future.
We're kind of riding a wave of potato genomics right now. 2 years ago, the first potato genomes for these tetraploid cultivars were released, and I think in this year we're expecting 100 to be released. So it's really ramping up. And what we're going to find from all that information about what makes a potato, I honestly can't say yet.
Craig Dent from the Max Planck Institute for Plant Breeding Research in Germany there. You also heard from Sergio Tuso from Ludwig Maximilian University, also in Germany. To read more about the work, head over to the show notes for a link to their paper, where you'll also find links to all the other stories in this year's clip show. Next up, it's Lizzie Gibney with her pick.
Astute listeners out there might already know that 2025 has been the International Year of Quantum Science and Technology. At Nature, we've enjoyed bringing you some quantum history, some myth-busting, and personally, I've been asking lots of questions about what quantum physics tells us about reality. But undoubtedly, for me, the highlight was in June when I got to go to this tiny German island of Helgoland, or Heligoland to us English speakers. It was for the biggest quantum party of the year, an event that was designed to mark 100 years of quantum mechanics. And in the piece, we'll get into whether that's a legit anniversary or not. But what I can say is that it really was just unlike any conference that I've been to before. For this piece, Ben grabbed me for a chat between sessions, and we covered everything from the latest in quantum computing to, just what happens when you trap a load of Nobel laureates on an island. I thoroughly enjoyed it, and I hope you enjoy being taken back there too.
Lizzie, how are you doing?
I am well. I am struggling with island internet issues, but thoroughly enjoying being surrounded by hundreds of quantum physicists.
So Heligoland is where you're at then. Paint pictures with words for those of us who haven't been there, because this is quite a small island off the northwest coast of Germany, right?
That's absolutely right. It's in the middle of the North Sea. It was a 4-hour ferry to get here from Hamburg. The weather is currently beautiful, but it was absolutely hellish getting here. It's tiny. You can run around it, as I did this morning, in about half an hour. Beautiful red cliffs full of native seabirds. It's really out here on its own. There's about 1,500 people here normally, and we have about 300 quantum physicists, so pretty high physicist to islander ratio at the moment.
And it sounds like potentially maybe a somewhat random place to hold a quantum physics conference, but the story of why it's being held on this island is a beautiful one, right?
It is. So let me take you back almost exactly 100 years to 1925, when physicists, were starting to paint a picture of the atom and trying to understand lots of experimental results that had come out and trying to bring together what we now know as quantum mechanics. And Werner Heisenberg, who was a physicist, he was then just 23 years old. He came to this island. He was escaping from some extreme hay fever that he had. Apparently, the sea breeze and the lack of trees, although there are many trees here now, I note, made for a good place to escape with hay fever. And the legend has it, and I have to say, I think it is quite a legend. We had some great talks from historians on the first night saying it may not have been exactly like this, but anyway, don't let the truth get in the way of a good story. He was unable to sleep. He had this kind of epiphany about how to reconcile these conflicting mathematical predictions with measurements about how the electrons are around an atom. And what he realized was to focus on just what's observable. And what's observable is when the electron is in different energy levels. So he invented this kind of mathematics which just looks at the leaps that the electron makes rather than actually thinking we can ever figure out its trajectory the whole time. Let's just focus on what we do know. And he came up with a way called matrix mechanics. It's a bit like you multiply in tables rather than just in a line. And that allows you to do these calculations. So that all happened here. And of course, as we know with science, it's very rarely actually just one person's contribution. When he got back to dry land, he worked with a bunch of collaborators to actually kind of turn this into a formalism, when they call it like the real mathematics of quantum physics. But essentially, that's why we're here. We're all trying to get a little bit of that zhuzh to rub off on us, a bit of genius from the island of Heligoland.
And so there's, as you say, 300 quantum physicists on this island. Then what's the vibe?
The vibe is great. I think everyone is so thrilled to be here. Everyone was ecstatic to get off the boat for a start. Once the seasickness wore off, everyone was just thrilled to be alive. We've got, I think, at least 4 Nobel laureates here and people who've done really, really phenomenal stuff. And they're all here. And because of the nature of the conference, we're pretty much trapped here. So they're just around and you can go and talk to them, and people just go off after, conference session finishes and have some lunch together. And I guess the idea is that hopefully there are new collaborations and revelations being found here.
I mean, that's a good point, because I was going to ask you what the kind of thrust of this conference is. Is it a celebration of the past, or is this an academic conference where new results are being put forward?
It is 100% an academic conference. At the conference dinner the night in Hamburg before we all came out here, Jack Harris, one of the organisers, called it quantum physics' birthday party. And of course, what would you want as a physicist in terms of your birthday party but to hear from all of your colleagues and friends about what they're up to? So there has been some debate. Something that I'm particularly interested in and which feels very fitting here on the island is discussion of interpretations of quantum mechanics. So famously, quantum physics, the maths works very, very well, but it's incredible to hear how some of these minds think very differently about what it actually means if we try and strip it back to the level of reality. We talk in an intuitive sense. They all completely disagree on that. So we've had a lot of talks on that, which do hark back a little bit over the 100 years, because some of the debates are still the same as they were in 1925. And we also have lots of other discussions, for instance, of people who are working towards trying to measure quantum gravity. So the fact that we don't have a continuous continuum of light. We actually have it in little packets in photons. And the idea is, what if is gravity actually like that? Would it be possible to quantize gravity? So people are working towards that. Not there yet. Can't make any grand announcements. But so we've got extremely cutting edge discussions, as well as some of that reflection on where the field has got to after 100 years.
Of course, you're there in a full reporting capacity. What else has caught your eyes and ears when you've been on the ground?
Well, a session I just came out from actually was really interesting. It was a physicist called Markus Arndt, who's at the University of Vienna, and he's working at trying to observe quantum superposition, which is where you are effectively in two quantum states at once, and you never actually directly see that happening, but you see the results of it because you get interference between those states and then you observe the final state. And he's trying to do it with ever heavier things. So he's done clusters of thousands of sodium atoms, so that's kind of like metallic clusters, and they're getting bigger and bigger. And he was talking today about the path towards proteins, antibodies, and that's the trajectory that they're going towards. And yeah, that one was absolutely fascinating.
So they're trying to entangle everything. Is that the plan?
So I spoke about quantum interpretations before, and that is one of the questions is, like, if you were entangled, what would that feel like? What would that be like? Like, depending on how you view quantum physics, some don't think that there is a boundary between the classical world, macroscopic world that we live in, and quantum. But the question is, how big a system can you get to be in a superposition or entangled? And we really don't know. And depending on how you view the underlying reality behind quantum physics, you might have a different answer on that. And so that's something that they're trying to push. It's an experiment that actually might help to tell us something about reality.
Well, if we can talk about reality for a moment, of course, quantum physics is everywhere, right? You think about quantum computing, for example, and it's in many cases been promised as the solution to solving many of the problems that face us in a variety of different fields. How much chat has there been about the practicality of things and maybe about the realistic nature of getting from X to Y? Because, of course, solving these problems are a ways away with things like quantum computers.
Yeah, there was a great talk on quantum computing from Misha Lukin, who's at Harvard, and he's using neutral atoms as the quantum bits in his quantum computer. And they had some quite impressive results in terms of how they control the qubits, because you want them to be able to talk to each other and you want to be able to shift them around. You want to be able to correct their errors. That's a huge issue in quantum computing, is that you naturally have your qubits fall out of their quantum state, and that ruins your calculation. So you do this idea where you kind of hook them all up together and you make a big quantum state that's much more stable, and it's called quantum error correction. And he was explaining how that works. So there are some really practical, of course, ways of using quantum physics. And that's one of the strange things, is that it really works. Like the maths of quantum mechanics is in everything already. It's how we make lasers. It's why an MRI machine works. It's in a transistor, that is at the heart of just a normal computer. Like, quantum physics is absolutely everywhere already. And the more and more we study it, the more just we know that seems to be true, that all the equations work. Which is why personally I then find it fascinating to know that whilst that is true, we still don't quite get what's going on.
Lizzie's travel log there. Check out the show notes for a link where you can find out more about her trip. In the middle of each week's Nature podcast, we have a couple of short, sharp science stories known as the research highlights. More often than not, they're read by Dan Fox. And here he is with a couple of his standouts.
This year, I've picked some research highlights that I think would make for interesting gifts this holiday season. A tiny robot capable of triggering chemical reactions, and some ancient Mesoamerican figurines. Researchers have developed a tiny robot that can manipulate minuscule drops of liquid. Scientists in a range of fields routinely need to move, split, or merge drops of liquid. Magnetic techniques can be used to do this, but these methods typically have either limited capabilities or a tendency to contaminate the droplets. To address this, a team developed a droplet manipulating robot about the size of a pencil-top eraser. To do this, they incorporated magnetic particles with sugar crystals in a flexible, soft polymer. Dissolving the sugar left holes, increasing the surface area of the polymer and its ability to adhere to droplets. Finally, they modified the surface so that the tiny robot would attract droplets, while being remotely controlled using magnetic fields. The researchers demonstrated various applications, including bringing droplets together, in some cases starting a chemical reaction, and splitting large droplets into smaller ones. This robot can control droplets at a microliter scale, but a future version might be able to manage nanoliter ones. Read that research in full in Nanotechnology and Precision Engineering. At the top of an ancient pyramid in what is now El Salvador, archaeologists have discovered 5 puppets with faces that either smile or scowl, depending on the viewer's perspective. The 5 clay figurines measure between 10 and 30 centimeters tall and date to around 400 BC. 3 of the puppets even have movable heads, much like modern dolls. The puppets' position on top of a pyramid and their orientation suggest they were used in rituals such as funerary practices or public ceremonies. The puppets have striking facial expressions that shift depending on the angle from which they are viewed. From above, they seem to grin. From eye level, they appear angry or disdainful, and from below, they look scared. The authors say that similarities between the puppets and artifacts found in other Central American countries suggest that some rituals and customs were shared across the region, challenging the view that the ancient inhabitants of this site were culturally isolated. You can view that research from any angle over at Antiquity.
"2025 has been another huge year for science, and I feel privileged to have been there to report on the highs and the lows of the last 12 months. It was genuinely difficult to pick one story for this show. There were so many I could have chosen. The mathematics of super dense crowds, how AI can help restore damaged paintings, or the researchers who 3D printed wasp-like insects to learn about the evolution of animal mimicry. The list goes on. But the story I've chosen is one that could, if it proves to be effective, make a real difference to a huge number of people. When I first saw this paper, I was like, that's an unusual approach to doing that, which is often a good sign that there's an interesting story to tell. From our 21st of May show, here's my pick of 2025. First up, we've got a story about efforts to improve the ability of anti-mosquito bed nets to prevent malaria transmission. Now, malaria is, of course, a scourge of humanity, with millions of cases seen each year, resulting in hundreds of thousands of deaths, with the burden of cases disproportionately seen in Africa. Progress in tackling malaria had been seen since the year 2000, with the mass use of insecticide-treated bed nets being one of the key drivers. These bed nets prevent people from being bitten and also kill any mosquitoes that land on them, lessening the risk of further transmission. But this control strategy has its limitation, as Flaminia Cataruccia from the Harvard T.H. Chan School of Public Health in the US explains.
Insecticides work very well for a while. So these bed nets are really effective for a while. We see a decrease in the number of mosquitoes and a consequent decrease in the number of malaria cases every time new bed nets are given to people. However, after a while, mosquitoes, they start developing new mechanisms of resistance, so they're not killed anymore, which means that they lose efficacy in terms of their ability to reduce the number of malaria cases.
Indeed, widespread mosquito resistance to insecticides is thought to be an important factor in the plateauing in reductions of malaria cases. And so researchers have been trying to come up with alternative strategies to get around it.
We thought, why can't we, let's say, get out of this concept that we need to kill the mosquito in order to control malaria? After all, mosquitoes don't cause malaria, they transmit it, but the causative agent is the malaria parasite. And in people, we killed malaria parasites with drugs. So couldn't we use the same strategy in the mosquitoes that transmit them?
And this is what Flaminia and her colleagues have got a paper about in Nature this week. Essentially, their method involves treating mosquitoes for malaria, using drugs to kill parasites before they can be transmitted to a human. They hope that these could be incorporated in bed nets to reduce the chances of malaria being spread. Now, treating mosquitoes might seem like an unusual approach, but the team have shown it is a possibility. In previous work, they demonstrated that the antimalarial drug atovaquone could work in mosquitoes to kill Plasmodium falciparum, the deadliest species of malaria parasite and the most prevalent on the African continent. However, atovaquone is a drug used to treat malaria in humans, and the team wanted to find other compounds that could do the same job but weren't used clinically. This wasn't an easy task.
No compounds were known to target the parasite in the mosquito stages, so we had to perform a screen. We gave mosquitoes a number of chemicals, and then we tested whether they would be effective against the parasite.
Of course, the team didn't choose these chemical compounds at random. Instead, they tested ones that had shown promise in human blood experiments. Specifically, these compounds targeted parasites at a certain asexual stage in their life cycle. The team reasoned that these compounds might show efficacy against a different asexual stage of the parasite's life cycle, one that takes place in the guts of female mosquitoes, specifically Anopheles gambiae, the most important vector for malaria in sub-Saharan Africa. Sadly for the team, there isn't a lab model for this stage of the parasite's life cycle. So, rather than test the activity of these compounds in a dish, the team had to manually test each of the 81 they looked at in this paper on live mosquitoes.
I suspect that we did thousands and thousands of mosquitoes. But so we take mosquitoes, we put them asleep, and then we apply the compounds individually. Then when they wake up, we put them in a cage and we feed them with malaria parasites. After a few days, parasites are developing, and then we dissect the midgut, which is where the parasites develop, and we count parasites.
Some of these compounds were absorbed through the insects' bodies and were effective at killing the parasites. But the team needed to test whether these promising compounds also worked in a way closer to how these insects would be exposed to drugs in the real world, namely through their legs when they land on something. In this case, the team used glass slides.
When we tested the compounds in this way, most of them did not work because the mosquito legs are covered by a waxy layer that is not easily penetrable by many compounds. And that's where we had to do a lot of work in collaboration with chemists to modify the structure of compounds to make them more easily absorbed by the mosquito.
Ultimately, the team developed 2 potent compounds that could be absorbed through mosquito legs. These targeted 2 different sites within the parasite's mitochondria, and the team hoped that using them in tandem will help lessen the chances of resistance arising. But there was more work to do.
We had these 2 compounds that were very potent in glass slides, but that doesn't really help us. We wanted to put them on surfaces that are more representative of mosquito nets. And so for that, we worked with material scientists that incorporated these compounds onto small surfaces, and these compounds retained full activity even when incorporated onto materials that are like very similar to actual mosquito nets.
These compounds, which Flaminia says are straightforward to synthesize and relatively cheap, maintain their activity after a year when incorporated into different sorts of plastic film, prepared in similar ways to how real bed nets are made. The compounds also provided a lasting protective effect in the mosquitoes.
What we found is that the duration of the effect is quite long. And 4 days later, the mosquito would have a much reduced chance of becoming infected with malaria parasites, which is something that is very promising for our control strategy, where a mosquito bites today and then she gets infected in 4 days and she would still be fully protected from infection.
Fredros Okumu is a malaria biologist at the University of Glasgow in the UK and the Ifakara Health Institute in Tanzania. He was not part of this research and was impressed with what the team have shown. He says that it could be a useful weapon to help bed nets maintain their impact, giving time for other economic or medical prevention methods, like vaccines, to be developed.
Insecticide-treated bed nets are our best hope at the moment in terms of vector control. But they have a very clear challenge that from an evolutionary perspective, we know we will not win. So what we got to do is find options to delay that loss and preserve the efficacy or the impact of those bed nets as long as possible. And I think this group are providing just one of the many options that we could use to do that. And they're doing it unconventionally. I mean, most malaria deaths are happening in very rural places, far from reach of health facilities. And they're saying, well, mosquitoes still go to those villages. So why should we wait for these people in the clinic? Why don't we bring the clinic onto their bed net? And they're doing it elegantly, and it seems to be working.
Fredros says that boosting the ability of bed nets could reinvigorate their two-pronged benefits, not just protecting the person under the net, but the wider community, something that insecticide-treated nets do by killing mosquitoes, but are being hampered by the rise in resistance. However, he thinks there remains important work to be done to investigate how well this approach ultimately works.
Right now, we can't call it 100%. What we have to do is to wait until these bed nets are tested in a real field setting, because we don't know what other problems might arise. But I would hate to see it just stay in the lab, because from what I can read of this paper and from the work that this group has done before, it's not only an elegant way to do things, but it's also evidently very transformative. And I wish them well.
Flaminia says that real-world testing is something that has recently begun, with a small trial using actual bed nets in Ethiopia and Burkina Faso. The team are also looking to make the chemistry required to produce these compounds cheaper and come up with ways to speed up methods to develop and test other compounds to increase the pool available. Only time will tell whether this strategy will help reduce the terrible impact of this disease, but Flaminia hopes it can be an important tool in the armory.
This strategy is not a silver bullet that will eliminate malaria from the world, unfortunately. Malaria is a very complex disease, and we have been trying to eliminate it for so long with many different tools and still here. So I think that this is one strategy that can really contribute to bringing parasites to elimination in certain regions by targeting the parasite rather than the mosquito.
Flaminia Katarucha there. You also heard from Fredros Okumu. To read Flaminia's paper, look out for a link in the show notes. Let's round out this year's clip show with a story we talked about in the briefing chat. Here's Shamini Bundell with her pick.
For this wonderful season of cheer and goodwill, I've picked an admittedly somewhat gruesome story, not for the faint of heart. When Ben asked me to go back and pick a story, I went through our old briefing chats, and this was such a fun story. And I do like a bit of archaeology. And this one, it's got everything. It's got bones, it's got lions, it's got visions of ancient Roman gladiatorial combat. It's some fascinating science. Here you go. Finally on the show, it's time for the briefing chat, and I have been reading a BBC News article today about a Roman gladiator in the northern English city of York who was found with lion bite marks on his bones.
Oh, this is sounding great. So I'm from a different place in the UK, Colchester, which was a Roman town, so I love all things Roman related. And so we've got gladiatorial combat, Shamini. Tell me about this one.
So gladiatorial combat, I've also been reading, like really, really popular throughout the Roman period. And obviously the Roman Empire spread a long way, reaching all the way to York, for example, which was apparently quite a big deal. It was the second most popular centre in Britain after Londinium, as it was called then, now London. And archaeological excavations have been going on in York, and they found this particular collection of bones, sort of graveyard. And because of the type of bones, we're talking sort of young men, signs of injuries, signs of a lot of musculature. They were very sort of well muscled. They think that this could have been a gladiator graveyard.
Wow.
And this particular bone, had these particular injuries, bite marks on the pelvis. And they were like, what could it have been? And they were struggling slightly. So they actually got some help from London Zoo, which has a collection of big cats, to try and find out which bite marks from the modern big cats best matched the marks on this pelvis bone. And they think, this was a lion that had bitten into this person's pelvis.
Well, two things. One, ouch. And secondly, is this an exciting finding? Because I assumed that you look at all the pictures and you look at the hit Hollywood movies, that gladiators are fighting wild animals all the time, right? So is this an exciting finding?
Yeah, it was definitely known from writing, from art, that you had these huge spectacles. You had gladiators mostly fighting each other, but occasionally fighting different kinds of beasts. And we also knew that very wealthy Romans who would often put on these spectacles were bringing in these animals. And, to think even to bring an animal like a lion into the centre of Rome would be a pretty impressive display of wealth and, potentially a lot of people who'd never seen a lion before. But there was never any actual evidence from bones before. We've never actually found bones with lion tooth marks in. And the fact that this is in York as well, which again, we know that there were wealthy Romans in York, and we know that these games and events were so popular that in a way it's not surprising. But, well, for one thing, there's a question of how they got a lion to York. And also, this would suggest, if these people are gladiators, that there is somewhere under the current city of York a Roman amphitheatre that we haven't found yet.
Oh, wow. So like a Colosseum-like space for these spectacles to take place. Goodness me. And if we talk about the individual who was bitten by this lion, of course, research has come such a long way in post-mortem examination, I suppose, of very, very old remains. Do we know if this is the bite that did for this person? Presumably it wasn't too good for their health, but what do we know about it?
So, interestingly, they did show that the bite did happen around the time of death, not after death. They can tell that. But interestingly, the fact that the bite marks are on the pelvis suggests that this wasn't a lion who was necessarily leaping to attack, because it would usually tend to go for somewhere like the neck. There are different sort of areas of the body where a lion would be likely to attack you if it was kind of going for it. So actually, the researchers who've been writing their paper about this, they suggest that maybe the gladiator was incapacitated in some other way, and then the lion went in and maybe dragged him away by the hip.
Goodness, what a finding. And as I say, I'm so surprised that this is the first one of these. Is this revealing anything that we didn't previously know about Rome and the Roman Empire?
Well, the finds of these gladiatorial skeletons broadly are telling us about their short and somewhat brutal life, as one of the people quoted in this article comments. In fact, this particular person, male between 26 and 35, had already different injuries, shoulder and spine injuries, which may have been from combat, may have been from some sort of hard physical work. So in general, we're kind of starting to build an image of what life was like for gladiators in Roman times. And in this particular case, kind of figuring out what Roman life was like in York, so far away from, you mentioned the Colosseum in Rome. One of the researchers quoted in this article likens the Colosseum to the classical world's Wembley Stadium of combat. And he says it's remarkable that they found this first bone-based evidence for this gladiatorial combat so far away from the Colosseum of Rome.
Well, I can say I am entertained, Shamini, by that story.
Reference.
Shamini and I chatting back in April there. You can find a link to that story and all the others you've heard today in the show notes. And that's it for this year's Clip Show. And that's pretty much it for this year. Thank you, as always, for being with us over the last 12 months. If you've enjoyed what you've heard, it'd be great if you could leave us some stars or a nice review wherever you get your podcasts. I'll be back later this week with a long read, and next week we'll have our traditional crystal ball gazing show where we look at what science might have in store in the next 12 months. But for the meantime, I've been Benjamin Thompson. Thanks for listening.